Hi, glad you're able to make it and watch this video about solving trigonometric equations using the unit circle. We're continuing that. We're at the last video for this section 13.2, and what we're going to focus on this video are trigonometric equations in which you use quadratic techniques to aid in finding solutions. So here's what I'm talking about when I'm referring to equations where you need to use quadratic techniques. There are many trig equations where it just necessarily happens that you have a trig ratio squared, okay? So that's what I mean by quadratic, just like you have an x squared or an m squared or an n squared or something like that. And we can solve these equations that have squared trig ratios using the same techniques that you use to solve polynomial equations. And of course, blending that with what we've learned about using the unit circle in order to solve trigonometric equations, and you'll understand how that blend works momentarily. Alright, very simple. The way I'd like you to try to solve equations in which you have trig ratio squared is treat it as though it were a polynomial equation. Alright, so instead of, for instance, sine squared of theta equals 3/4, maybe you could treat this as x squared is equal to 3/4 and think about what would you do to both sides of the equation to solve that. And of course, what you would do is take the square root of both sides, right? We could say x is equal to plus or minus the square root of 3 over 2. And we're going to use the same technique here to get sine of theta by itself. We're simply going to take the positive and the negative square root of both sides of the equation. So this will become the sine of theta equals plus or minus the square root of 3 over 2. Alright, now as soon as you've been able to get the trig ratio by itself, now, there's one thing that's going to be different compared to other trigonometric equations, but the rest is just solving trigonometric equations. We have two different solutions, and I would like you to think of those separately, make them separate equations actually. So we have one equation in which we're going to say the sine of theta would equal the positive square root of 3 over 2, and we're going to find all the values of theta between 0 degrees and 360 degrees that would make that true. And then we're also going to think about what are all the angles theta between 0 and 360 whose sine would equal the negative square root of 3 over 2. Alright, so we're separating into two different equations, and we're going to solve each individually. Alright, now let's focus on the first equation, or it says the sine of theta equals the square root of 3 over 2. Between 0 and 360 degrees, there are two places where that's going to be the case, and that would be at 60 degrees as well as at 120 degrees. And so from the first of the two derived equations that we ended up with, we're going to say that theta equals 60 degrees and 120 degrees. Those are the solutions there. And then we're going to focus on the second equation where we're trying to figure out what values of theta will make the sine of theta equal to negative square root of 3 over 2. And as you can imagine, those are just reflections in the x-axis of these two values. 300 degrees right there, as well as 240 degrees right there. Alright, so we got two different equations with their pairs of solutions, and typically you'll write it all as one set of solutions. And I tend to do that from least to greatest, although that's not really necessary. There you go. Alright, so that's solving the simplest of the trigonometric equations that you can solve where quadratic techniques are involved. Now we're going to make this a little bit more difficult gradually as we go through the video. Alright, so here's the next one we're going to solve, still on the same interval from 0 to 360 degrees. Alright, now the next thing I'm wanting to do, this equation we could actually solve two different ways. Alright, one of the ways is we can try to get cosine squared by itself. And this is probably the easiest way, probably the method that you're going to use most of the time for an equation of this difficulty level. So we can say 4 cosine squared of theta equals 1, and then the cosine squared of theta is equal to 1/4. And then here's where we're thinking of that. What if it was x squared is equal to 1/4? Let me put a theta in there, hold up. What if x squared was equal to 1/4? What would you do? Well, you would take the square root of both sides, and you would get, well, x equals plus or minus 1/2. Here we're going to get the cosine of theta is equal to plus or minus 1/2. And then you'll separate it into the two different equations. Cosine of theta is equal to positive 1/2, and cosine of theta is equal to negative 1/2. Now coincidentally, these are the same solutions that we just got overall. Whoops, didn't mean to draw that, trying to highlight. If we're solving the equation cosine of theta is equal to 1/2, the two places where that occurs between 0 degrees and 360 degrees are at 60 degrees and 300 degrees. And if we look at the equation cosine of theta is equal to negative 1/2, well, we'll get the reflections of those same angles, but in the the y-axis. Right there at 120 degrees and right here at 240 degrees. And so here's your overall set of solutions. Make sense? I'm hoping so. Now I said that there are two different ways that you could solve this particular equation. I want to go ahead and show you the other method right here. And either one is fine, whichever you find easier at the time that you see the problem is the one that you ought to go with. Let me erase the work here. I'm going to leave the solutions because we're going to end up getting the same thing ultimately. Shouldn't matter what method you use as to what the solutions are, should it? All right. And so here's what I want you to take notice of. Let's say that I hadn't gotten cosine squared by itself, and I kind of treat that as though it was a 4x squared minus 1 instead of a 4 cosine squared theta minus 1. Well, we're trying to apply quadratic techniques to solving these trigonometric equations, and one of the quadratic techniques that you use whenever you can is factoring, right? And this happens to be a difference of squares pattern. You could factor 4x squared minus 1 into 2x minus 1 times 2x plus 1 is equal to 0. And then you could set each individual factor equal to 0, right? Well, we can do the same thing here with the trig values. 4 cosine squared theta is a perfect square, so is 1, so that's a difference of squares pattern. And you could simply factor that then into conjugate pairs. 2 cosine theta plus 1 times 2 cosine theta minus 1. And then you set each factor equal to 0. And then solve those equations separately. Here you would end up with subtracting 1 and then dividing by 2. So you get cosine of theta is equal to negative 1/2. Right? Isn't that one of the equations we solved a moment ago? That's where we got the 120 degrees and the 240 degrees from. And then your other equation, you would solve by adding 1 to both sides and then dividing by 2. So you get the cosine of theta is equal to positive 1/2. And that's the equation we solved using the other method that produced the 60 degree and 300 degree results. All right, so factoring is a valid method for solving trigonometric equations from time to time when quadratics can be applied. And in fact, that's what I'm going to try to do with this equation right here. All right, now I've switched from degrees to radians. Now we're going to solve the equation on an interval from 0 to 2 pi rather than 0 degrees to 180 degrees. All right, but you see the equation that we're trying to solve. The thing that's different about this one is it doesn't just have a tangent squared. It's got a tangent squared and a tangent term. So it's basically got a quadratic and a linear term if I want to relate this to polynomial equations. And that's exactly what I'm trying to do here. Now, I'm not going to use x just because of my angle is called x here, but let's say I use the letter u instead to help you see what we're going to do with this one. Rather than this being 3 tangent squared x plus 4 tangent x plus 1 is equal to 0, let's pretend this equation was 3u squared plus 4u plus 1 is equal to 0. All right, so this is an instance where you really have two choices. And I'm going to work them out both ways to tell you the truth. You really have two choices as to how you'd find the value of u. One of them is factoring. All right, and so I'm going to use guess and check method for factoring here. This turns out to be one where you can guess and check pretty easily. Now, hopefully you see kind of what I've already started. If I know that I'm going to multiply two factors together and get 3u squared, I know that one of them is going to have to be 3u, and the other one is going to have to be u. All right? And then if I'm going to multiply two values together and get 1, well, it either has to be positive 1 times positive 1 or negative 1 times negative 1. And then I'm just going to put a plus here because obviously it's positive 1 since this is a plus for u here. And just double check that this actually gives me what I'm looking for right here. 3u times u is 3u squared. 1 times 1 is 1. We already said that. If you multiply your outer terms, that gives you 3u, and if you multiply your inner terms, it gives you 1u, and 3u plus 1u is 4u, right? Not trying to teach you quadratics here. You've factored many times, but we learned how to factor by grouping in that instance. That's why I wanted to show you that method right there. Well, we could go ahead and treat the original equation kind of the same way. All right, now we didn't have u's, we had tangents, but we can still factor 3 tangent squared x plus 4 tangent x plus 1 the same way that we just factored that 3u squared plus 4u plus 1. All right, we can make it into 3 tangent x plus 1 times tangent x plus 1. Still equal to 0. All right, you see how that's working? And then we'll set each individual factor equal to 0. So there's one of the equations we'll end up solving, and the other one, of course, tangent of x plus 1 is equal to 0. So that's the quadratic part of solving this equation. Now for the trigonometric part, I'm going to go ahead and start with the second of those equations. Tangent of x plus 1 is equal to 0, which would result in us saying that the tangent of x is equal to negative 1. And let's think about where on the unit circle between 0 and 2 pi you have a tangent that's equal to negative 1. That'd be wherever you have opposite sine and cosine values. 2 places, right here at 3 pi over 4. And then remember, angles with equivalent tangent values appear at opposite ends of the same diameter, or they're pi radians apart from one another. So if I add pi to that, 7 pi over 4 is the other place where you'd have a tangent that's equal to negative 1. So there are 2 of our solutions. Now for the second equation, you're about to see something that I haven't shown you before. We're going to subtract 1 and then divide by 3. That's not the part you've never seen before. We're going to get the tangent of x is equal to negative 1/3. But what you haven't seen before, from me at least, is you haven't seen an equation where our sine or cosine or tangent was equal to some value that we haven't memorized. We don't know, based on the part of the unit circle that you've been asked to memorize, what angle would have a tangent of negative 1/3. And so I'm about to instruct you on what you can do to overcome that fact. Well, it's going to kind of go back to what we learned whenever we were just doing triangle trigonometry instead of circular trigonometry. If you knew the tangent of an angle, you could find out what that angle is by taking the tangent inverse of that angle, correct? Now, I want you to do that. We're going to round to 3 significant figures here. But I want you to go ahead and type that into your calculator. So this would have to be a calculator problem for you to be able to get this set of solutions. Forgot to write my negative there. That's the tangent inverse of negative 1/3. We got plenty to discuss with this. To 3 significant figures, that's going to tell us that x is approximately negative 0.322. All right, now here's what we have to discuss with that. First of all, whenever you type in a sine inverse or cosine inverse or tangent inverse in your calculator, it's only ever going to give you one value. That doesn't mean that that's the only value that you can use. And there's things that you don't know about the domain and range of an inverse tangent function, for instance, that made this one, for instance, give me an answer that I can't actually use. Right? Isn't x between 0 and 2 pi? And negative values are not between 0 and 2 pi, are they? However, even though this can't actually be a solution, and I'm going to cross it out, it's not a solution, we can still use it to help us find the solutions. Just think about where negative 0.322 would be on the unit circle. Now, if we're dealing with decimals, radians, here's 0, and negative pi would be negative 1.6 approximately, correct? So this would be about negative 0.8. We're talking about negative 0.3 being, well, basically right there. Really close to it anyway. Whoops, sorry, got that wrong. Negative pi would be about negative 3.14, right? So this would be about negative 1.6, and negative 0.3 is going to be closer to around there. So there's the angle measure that we got, although we said we can't actually use negative 0.322. Well, where are other angles that are between 0 and 2 pi that would have the same tangent value? Well, we know we can add pi to that and get the angle that's at the opposite end of the diameter, correct? So go ahead and take your calculator, add pi to the answer that you got. So that'll get you the angle at the opposite end of the diameter, and that in terms of radians is about 2.36 radians. Okay, now that is between 0 and 2 pi, isn't it? So that is a solution that we can use. And then let's see if there's an angle that's coterminal with negative 0.322 that is between 0 and 2 pi. And there is actually. If you'll just add 2 pi to this value, or add 1 more pi to this value, you choose, you'll get the coterminal angle for here, which is positive 5.50 to 3 significant figures. That is between 0 and 2 pi as well. All right, and so our solutions written as one solution set would be written as such. And again, I don't really care if you get it from in order from least to greatest, but that is the way that I wrote it right there. And I just kind of used my unit circle to figure that out, right? That first, and that, and that. Okay, now I mentioned that you could use quadratic formula for this. Due to the length of time that I've taken so far, I'm not going to show you how to work this problem with that. I'll just show you the next problem using quadratic formula. But that is certainly an option. Now, let's take a look at it. Let's solve this equation, sine squared x equals 3 sine x minus 2, using quadratic formula. Whenever you're solving quadratic equations, you have to set the equation equal to 0 to begin, don't you? And anytime you have a sine squared and a sine, a quadratic and a linear term essentially, that's where I want you to begin, is by setting the equation equal to 0. Now, what if there weren't trig ratios involved? What if there's just a normal quadratic equation? You could have it written as u squared minus 3u plus 2 is equal to 0. Now, I hope you realize that that's factorable, but I said I was going to use quadratic formula to solve. Well, so then you would find your solutions this way. You would say that u is equal to 3 plus or minus the square root of, well, negative 3 squared, right? So 9 minus 4 times 1 times 2, that's 8, over 2 times 1, so over 2. And you would get u equals 3 plus or minus the square root of 1 over 2, and you would solve from there, correct? Well, we're going to do the exact same thing here. We've got this thing set equal to 0, and we're just going to use quadratic formula along with it. Except instead of u equals, what's going to happen is we're going to say the quadratic formula is going to tell us what the sine of x is equal to. Now remember, with quadratic formula, you just plug in the coefficients of the terms into the formula. And I want to make sure you know what those are. Here, a would be equal to 1 because that's the coefficient for our quadratic term. B would equal negative 3 because that's the coefficient for our linear term. And then c would equal 2 because that's our constant term. All right, and it's really going to be exact same values that I just plugged in down here. All right, your opposite of b is positive 3. Your b squared is 9. 4 times a times c is 8, so you got minus 8. And then your 2a is equal to 2. Now what I'm going to do is simplify that. I think you can tell that that would give us the sine of x equals 3 plus or minus 1. Square root of 1 is just 1, right? Over 2. And then that's going to give us two separate solutions. If I say the sine of x is equal to 3 plus 1 over 2, that's going to be 4 over 2, or just 2. And then if I say the sine of x equals 3 minus 1 over 2, that would give me 2 over 2, which is 1. All right, so there's our two different equations that are going to give us solutions. And now we've got to start thinking trigonometrically instead of quadratically. Let's go to the unit circle. And let's start with this equation, sine of x is equal to 2. Now, I hope you're a little bit puzzled by that equation. Can you think of anywhere on the unit circle where the sine of x is equal to 2? I hope not, because the highest y coordinate you can get is 1, isn't it? There's no such place where the sine of x would be equal to 2. And sometimes that happens. You get equations that don't give you solutions. In this case, there are no solutions for that equation. Then let's look at the other equation. You got the sine of x is equal to 1. Now, you can find a place on the unit circle where the sine of x is equal to 1. And since we're talking about radians, remember that's what the directions were, 0 to 2 pi. We're dealing with radians. That's going to be at pi over 2 right here. Now, in order to get the next angle that has positive 1 as a sine value, I'd have to add 2 pi, which would give me 2.5 pi. That's too large. Or I'd have to subtract 2 pi, which would give me a negative value, and that's too small. Pi over 2 is the only solution on an interval from 0 to 2 pi for x in that second equation. All right, well, since one of the equations we had gave us no solutions and another one only gave us one solution, that means that the original equation here only has one solution, and that solution is x equals pi over 2. All right, so you've seen now how you can use quadratic techniques to solve certain trigonometric equations, and it's something I promise that IB is going to throw at you from time to time. So make good use of this technique. Thanks, guys, for watching. Later.